Sad face. Do you know why you should have a sad face on? This is it. My last video. That's it. I know, Brady. Calm down. I know, I get it. There's tissues over there if you need them. Nick, I get it. I understand. You're upset. And we've been so much together. 2 semesters of physics, some of us, right? Ian, I get it. But don't worry. You've got Bear to comfort you. And I saved the best for last. Dressed in my best. This is it. This is my best. This is why I go to Sunday church in right here, okay? Yeah. Saved it for the best for last. Now, I have to go through some things. A lot of things on my list. Actually, I had to make a list. There's so many little things that I had to, remember to go over that I haven't gone over yet. I've partially gone over. I need to finish them. So I made a list. Here's our list. Okay. There it is. Yep, that's the list of things I have to go over. It's going to take forever. Forever? Come on. I've told you 1,000,000 times not to exaggerate. Get it? 1,000,000 times. It's funny. Okay, let's go through. It won't take me that long. We'll go through this. Some of them are really quick. Some of them aren't. Some of them aren't so fast, but whatever. First one. The reason I wrote that down, I said lead 212. Notation. That just means that when you see an element with a number after it, that's the mass number. And there are different isotopes, so you could have different mass numbers. For example, another one for the example is carbon. Carbon 12. We all know that's good old high quality made in America regular carbon. But there's also carbon 14, which is radioactive stuff. Okay, carbon dating, hydrogen, nitrogen go to a dance on Friday night. That wouldn't be carbon dating, actually, it'd be hydrogen dating. Oh, funny! Now, so these are just the notation of the mass. So when you see that number after the element, it's the mass. Now, if we want to get the atomic number, if you don't have it memorized, you need a periodic table. And then if you want to get the amount of neutrons, you would subtract that number from that number from the mass. So for example, if it's carbon 14, you look up carbon, number 6, so 6 protons and 8 neutrons. Okay, that's it, moving on, first one done. Nucleons. Just wanted to mention that you'll see that word sometimes, that nucleons are the particles in the nucleus, okay? And we all know that there are protons and neutrons, those are the nucleons. Those are the nucleons, protons and neutrons. So, and the electrons on the outside. You said the electron can be on the inside and be ejected. You rocked my world with that. That's correct. However, they are ejected when one proton or a neutron changes back and forth. They're not hanging out there waiting, just kind of chilling on their own. They get ejected from a proton or a neutron. So a nucleon is just a proton or a neutron parts of the nucleus. All right, done with 2 of them. Pretty good. 3, strong nuclear force. There are 4 different fundamental forces in nature. You've got electrical force, electromagnetism actually, magnetic force, electromagnetism, grumpy loop is one. Electromagnetic force, gravity force, weak nuclear force, that's the radioactive stuff. That's radiation, that's what we're talking about. I mean, it's a weak force because these radioactive particles come out and they escape, so hence the weak nuclear force. A strong nuclear force is the force that holds those nucleons together. Those are the parts in the nucleus. So if you think about it, those things don't like each other. They're protons, all right? A proton and a proton. I'm positive. Oh, we're so optimistic. I'm positive, get it? Optimistic, funny. And you're going to miss the humor. Yes, you will. And so a proton and a proton, we have to make up a helium nucleus, so we got to get together, but we don't like each other. We don't, ew, gross, get away from me. See, they don't like each other, so how can I hold them together? You need some strong force to do that. A lot of strong nuclear, that's the strong nuclear force, holding those particles which do not want to be next to each other. They really don't like each other. And if we go back to the electrical unit, using Coulomb's law, we were not going to, but if we did, we'd find out there's a crap ton of force trying to repel those things when they're in close proximity. They do not like each other. So you get a strong force holding them together. And when you release that energy, that binding energy gets released. That's what you get out of it, okay? So that's a lot of energy there holding those together. That's called the strong nuclear force, holding those nucleons, which don't like each other, together, okay? Got that one done. Fusion in stars. I want to talk a little bit about that. Fusion, the best fusion reactor that we have is our sun, okay? Go out there, take a look at it, stare at it with your eyes open for about 2 minutes. Okay, do that. We got to hold them open, and you'll see the fusion going on. No, don't do that. Some of you are going to do that, and I'll get blamed for it, okay? I mean, if you do that, you deserve whatever you get, but don't do that. But if you did, I mean, you can't see the fusion going on. And if you think you can see it, I'm worried about you, okay? Maybe I can help you get some help. But you can't see the fusion. But the fusion's going on, and it's when a hydrogen and a hydrogen are fused, put together. There's fusion, putting together, and fission, splitting apart. Fission. I had a dream last night. I had a fission that all my students will do very well in this unit's test. Fission. Funny. Oh, man, I'm cracking myself up today. All right, so you've got fission, and then fusion. So hydrogen making helium fusion. Now, the thing is, though, it's not just, helium floating around, not floating around. The heliums are also in the sun when the fusion reactor is making these helium atoms, but those can be fused together as well. And fusion happens in a star like our sun, up to and through and including the element iron, up through iron. So things are fused through that fusion process from basic hydrogen up through and including in the sun, up through including iron. So that's where those elements get fused together. Now wait a minute, I know there's other elements beyond, iron. I'm pretty sure. I mean, there's like, zinc and krypton and lead and uranium, not my uranium. Yeah, and those are greater atomic numbers than iron. So where do those come from? Supernova. Yeah. Our sun won't supernova, not big enough. But big stars, when they go boom and go supernova, when they go supernova or nova or supernova, when they boom, that's when those things are forced together with a huge explosion to create those higher number elements in the periodic table that you see. That's where those come from, supernovas and novas. All right, and they're relatively rare. That stuff is, as you get higher and higher, you get relatively rare materials compared to the lower stuff, which is being fused all the time in a lot of stars. Okay, well, moving on. So we just want to give you a little hint on, fusion reactors, and the best one is up there. I mean, fusion would be great if we can get it on Earth and do it. I mean, there are some fusion reactors on Earth, but the problem is you go super high temperatures, super, like the sun, super high temperatures, in order to pull it off, okay? Do you want one of those in your backyard?
Well, it'll be warm all the time, or wouldn't it be cold in the winter?
I guess so. Okay, at least you got that going for you, right, Billy?
Right.
Okay, Billy's still angsty. All this time, Billy's still angsty. When's he ever going to change?
Never.
Okay, move on. So we have conservation of mass energy. Conservation of mass energy, not mass and nucleus. What I mean by that is there's the conservation of mass in energy, that law. What that means is the total amount of mass and energy will always remain the same. But that doesn't mean the total amount of mass will remain the same. We know E is equal to mc squared. There's something called the binding energy. Some of that mass, when things come together to form an atom, the protons and the neutrons, you end up losing mass because some of it is converted into binding energy. You need that energy. So conservation of mass doesn't hold, you ready for this, in nuclear reactions. In normal chemical reactions, absolutely true. Conservation of mass. That's why you got your balanced chemical equations, right? Conservation of mass, that's chemistry. But we're better than that. Remember, we're the apex predator here in physics, okay? And chemistry doesn't quite get it, okay? We do. We know that in a nuclear, gotta say it correctly still, a nuclear reaction, you get some loss of mass. So mass is not conserved in nuclear reactions. All right, some of this comes from converting energy. But the total amount of mass and energy, it remains the same. Just that you lose mass in a nuclear reaction. All right, just want to point that out. I mean, we've talked about that a little bit already, but just a good reminder. Remember that if you have a question that talks about, will there be a mass loss or something related to will there be a mass loss when you combine these masses? The answer is yes, you can lose mass because it gets converted into energy. Hence, physics is more awesome than chemistry. Okay, moving on. Here we go. Quantum atom energy levels, and I put ladder rung. Okay, that's how I explain this. Okay, let me draw this out for you real quick here. So let's say that we have some energy levels in an atom. You're good? You can see this. And maybe this is a -4. I'll put EV. A lot of times these are given in electron volts. We know the joules of the International System of Electron Volts are commonly used, especially when doing these, what are called the modern Balmer series. Sometimes this is called, when you're talking about hydrogen, hydrogen has what's called the Balmer series, and those have different lines, absorption lines. What are you talking about? Hang on. So this is, let's say this is a 2, a -2. What are these things? -1. I don't get what you're doing. Just calm down, all right? Just wait. Ay, caramba. Yeah, copying this down will doggone you better, trust me. All right, EV. Now, what this is talking about is this is energy level 1, 2, 3, 4.
Oh, I remember something like this in chemistry. Different energy level numbers. 1, 2, 3, 4. No, different amounts of electrons and their sublevels. And
Yeah, you're right. That's what it is. Energy level 1, energy level 2, energy level 3, energy level 4. Okay, now we're talking about energy level 1. This is closest to the nucleus down here. Then you get farther and farther away. Now, well, what are these? These are the energies that it takes to move to a different energy level, or the amount of energy that you need to go back down that you're going to give off. If you're going to go from here to there, you're going to need energy to do that. I call it the ladder rung. Ladder rung, what do you mean? Well, if I'm on a ladder and I want to get to the next rung, I got to put energy into the system. That's me. I got to work, so I'm going to lose energy. But I have to do some work. I have to go from here to there. So I have to put some energy into the system to do that. You're not going to go from here to here unless energy is put into the system. So when I go from here to there, I have to use some energy up. If I go from here to here, I give off some energy. Now we're talking about potential energy, and that's why the negatives are in here. The negatives are here to say that if I go from here down to here, I'm going to give off, hence the negative amount of energy to do that. So down here, if you're an electron, and here's the nucleus down here. Here's the protons. This is where you want to be. This is where you want to be. You want to be down here near this. And so if you get closer to where you want to be, you lose energy. Your potential energy goes down. Think about it. This is gravity. If this marker here has potential energy rather than my hand, okay, the closer it gets to my hand, the less and less potential energy it has. It's losing potential energy. And that's what these negatives mean. You're losing potential energy as you get closer to an electron where it wants to be. Proton. All right, still with me? Okay, so that's what this means. These are energy levels, and they have some energies associated with them. In order to, if I drop from an energy level from here to here, okay, I'm going to give off a certain amount of energy. If I drop from here to here, a certain amount. If I drop from here to here, a certain amount. Okay, all right. Okay, that's what the negatives are there for. Okay, so now let's do some questions that you could see potentially with this quantized. Why is this quantized? What do you mean quantum? What are you talking about? How's the quantum atom? Oh, good question. Okay, quantum atom. If you are going to, okay, let's say you're at a Coke machine and you want to get a Coca-Cola, and it's $1.50, and you have 6 quarters. Do the math, that's right, 6 quarters, $1.50. You put 1 quarter in, hit the button, nothing. 2 quarters in, hit the button, nothing. 3 quarters, nothing. 4 quarters, nothing. 5 quarters, still I'm not getting my Coke. 6 quarters, boom, magic happens, hit the button, Coke comes out. Nothing's going to happen until you have the exact right amount of energy to make it happen. That's how Coke machines work. Coke machines are like quantum mechanics. Huh? Check it out. If I am an electron hanging out here, and I want to go to this energy level here, I'm going to need to have a certain amount of energy to do that. How much energy? Well, if I'm going from 4 to 2, I'm going to need 2 electron volts of energy to do that. As a matter of fact, I'm going to have to gain 2 electron volts, because if you go away from where you want to be, somebody's going to make you do that. Like, I want to be on the ground. If I'm going to go higher than the ground, something or someone's going to have to put energy in to lift me above the ground, because it's not going to happen on its own. So we need to have energy absorbed. Absorption lines, boom, absorbed. We need to have energy absorbed to go from here to there. How much? 2. How do you know that? Because look it, you can subtract. You're going to need 2 electron volts to go from here to here. Coke machine analogy. Well, what if I'm here and I gain 1 electron volt? Oh, boom. No, you're not going to make it. Coke's not coming out. What if I gain 1.8 electron volts? Oh, boom. No, you didn't make it. You got close. 1.9 electron volts. Oh, so close. Boom. No. Nothing happens. You're stuck. Magically, though, with 6 quarters, $1.50, Coke comes out. Magically, boom, 2 electron volts, you're there. What would happen if you had your Coke machine and you put in 1, 2, 3, 4, 5, 6, 7 quarters? 7 quarters, hit the button. What are you doing? You're getting 1 Coke.
What does that have to do with this?
What if I'm an electron here and I get jolted with 2.5 electron volts? That's more than enough to go to here, but would it be enough to go to here? To go from here to there, I need 3 electron volts. The difference of 4 and 1, subtract, do it, calculator time. What do you get? Yeah, 3. You need 3 electron volts. So if you plug in, if you put 7 quarters into your Coke machine, you're just getting 1 Coke. You're not going to get 2. If I put 2.5 electron volts of energy into this electron, I'm not going to here. I don't have enough. Okay? You're not getting the second Coke. You're coming right back down here. You're still getting your Coke, but you're going to have a little quarter left over, right? The quarter goes and drops out of the machine. With this, the energy, you drop down to here, and then the energy goes drops out into oblivion. Okay? Coke machine, pretty good example, huh? Boom, thought of it. Awesome. That's why I get paid $1.4 million a year. I was going to say billion, but that's next year with my raise. Okay, so this is why it's called quantum. You need discrete amount of energy to get something done. If you don't have that right amount of energy, nothing happens. And if you have more than enough of that energy, you're still only going to get one thing happening. What if we had an electron down here on the first energy level, and we zap it with 3.25 electron volts? Zap! You go, whoa! You get excited, right? When you get hit with energy, whoa! Excited. You're in an excited state. And you would go 3. That's 1, 2, 3.25. I need 3.5 electron volts to go to here. I see the difference between 4 and 0.5 is 3.5. I need 3.5 electron volts to do that. And I don't have it. I have 3.25. So where would I end up? Boom, energy level 3. Okay? Those are the kind of questions that you will get when talking about the quantized atom and energy level absorption spectrum, and emission. You can also get an emission spectrum, which is just the exact opposite of the absorption spectrum. What are you talking about? Let's say I had an electron here. Okay, electron here on the 4th energy level. And it doesn't like being up there. You know, like electrons want to be down closer. If you're on a very high ladder, do you like being up there?
No.
Well, yeah, nobody really wants to be a really high ladder.
I do.
Well, you're weird. Okay, well, most people don't. And so if you're up on a high ladder, what do you want to do? You want to come back down. Okay, so you get more stable. Ooh, down to the ground state. Yeah. And so if I'm up here, I don't want to be up here. So if I'm up here, I'm going to go, oh, hey, I'm going to go down here. Boom. Okay, ready? Boom. That's where I am. So now what just happened? I lost energy, hence the negative. I lost energy. How much energy did I lose? You're at 0.5, you're at 2, you lost 1.5 electron volts. You have to give off 1.5 electron volts to pull that bad Larry off. Okay? All right. So it's just the opposite. When you're emitting energy, okay, you're giving away energy, dropping down levels, it's the opposite of the absorption energy to go up levels. But you have to have and you give off only certain amounts of that energy. Okay, they have to be in quantized amounts. Okay, let's see. Let me do one more kind of an example with this. If we had an electron sitting here on the 2nd energy level, and that electron absorbs 1 electron volt. Absorbs 1 electron volt. Where would it end up?
It'll fall down here where it was to be.
No. I said absorbs 1 energy. Oh. Yeah, absorbs 1 electron volt. You end up here. Okay, on the 3rd energy level. That's where you would end up. Okay. If we have an electron sitting here and it gives off, 1 electron volt, where would you end up? Oh, careful. you give off 1 electron volt, where would you end up? Give off 1 electron volt. That means you're losing energy. It means you're going to drop.
Oh, you're going to drop down here.
No, because you have to give off 2 electron volts to end up down here. I said give off 1 electron volt. So where would you end up? Answer? Right where you are. You wouldn't end up anywhere. You haven't given off enough energy to get down here. You haven't earned it. So you give off 1, you're not going anywhere. Okay, so in other words, that actually wouldn't happen. You can't give off 1. You can't give off 1. If you're going to move, you can absorb 1 and go up, but you cannot give off 1 because it doesn't happen. It's like the Coke. You're putting your quarters in. You have 4 quarters, and you want to hit the $1.50 Coke button. Nothing's happening there. Okay, nothing's coming out. So you can't get anything done by giving off 1 electron volt here because there's nothing here, nowhere for you to stand. Those are the ladder rungs. Another way I think about it is you're climbing a ladder. Boop, 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 boop. You have to stand on a rung. You have no choice. Okay, you're on the first rung, or you're on the second rung, or you're on the third rung. And let's say the step ladder, you're on the 4th rung. Those are your choices. You're not hanging out anywhere in between. You can't. Doesn't happen. Okay? So if you're an electron here on the first rung of the ladder, and you get enough energy to absorb 1 electron volt, okay, that's kind of like, going up, putting your next foot in between the 2 rungs, okay? Now, where are you going to end up? On the first rung. You haven't had enough energy to get the second rung yet. So if you're here and you end up getting 1 electron volt, you're going to still end up here. You need 2 to get to there. Yeah, you can't stand on a half of there's no 1.5 rungs on a ladder. There's 1 rung, 2 rung, 3 rungs. The only places you're hanging out, you're going to lose or gain a specific amount of energy to pull that off, going up or down. All right, Kay? All right, you're going to get questions like that. Okay, all right. Okay, all right. I think I've covered that well enough. That was a long one, right? That's like took most of the video, but it was a long one. Okay, so quantum mechanic energy levels, ladder rung, absorption lines. These are absorption lines or emission lines, depending on which way the electron's going. Is it being going up or down? Okay, and last thing, kind of cool. See, always the same, time dilation. Talking about the speed of light. Speed of light is always the same.
We know that. You said that already. Electromagnetic spectrum, radio waves and gamma rays and microwaves, all light, so they all get the same speed.
No, that's not what I'm talking about. That's true, but that's not what I'm talking about. What I'm talking about is, no matter what your frame of reference is, the speed of light is always the same.
What do you mean?
So, for example, unless I'm just standing here and I turn a flashlight on, okay, what's the speed of the light coming out of the flashlight?
Well, obviously, 3.0 times 10 to the 8th meter per second, speed of light.
True. But what if you're traveling at the speed of light and you turn the flashlight on? What's speed of light now?
Oh, well, if I'm watching you do that, you're traveling the speed of light and you turn the flashlight on, it'll be twice the speed of light.
No, wrong. That's what's so weird about light. And I could go into a little bit more of this, how this all happens, but we need about another 8 hours and a PhD, and we probably still wouldn't get it. Okay, there's some things in life you just don't know. But anyways, here's the thing. Point is, no matter how fast you're going and you turn your flashlight on, that light is going to be traveling at the speed of light. Okay, so if you're traveling at the speed of light and you turn your flashlight on, everything is called relativity, then the speed of light is always the same, no matter what your frame of reference is. Here's something else kind of cool about light, though. That let's say you were traveling at the speed of light. There's something called time dilation. It's called the twin paradox. Okay, listen to this one, okay? Blow your mind. Last thing I'm going to cover in all my videos right here is blowing your mind, but boom, physics, okay? Don't do drugs, do physics. I've always said that, always will. So let's say that you want to travel to the nearest star system outside of Rome, the Centauri system, Alpha Centauri, Proxima Centauri, these little star groups cluster. I think there's 3 of them there. And so that's the closest exoplanet to us. And there's one in the life zone, by the way. And it was weird. They found this signal that's coming from there. They're not sure what it is, okay? Who knows? Probably aliens, but whatever. So you want to go explore Proxima Centauri and its little red dwarf life zone planet that's there. So you get in your light ship, and you travel speed of light. Speed of light. Okay, 4 light years away. So what that means is it'll take you 4 years traveling at the speed of light to get there. Star Wars gets this wrong. Star Trek would never get it wrong. Star Trek actually has good science. Star Wars is science. They talk about distance in light years. Yeah. No. Well, I mean, they do. They talk about time in light years. I'm not wrong. They talk about time in light years. I it's going to take you like 3 light years. You know, it's going to, like, come on, let's get moving. What do you, I don't got all this time. No. The light year is not a time, it's a distance. So if you were talking about a star system 4 light years away, what that means is, it's at a distance that would take light 4 years to get there. 4 Earth years to get there, traveling at the speed of light. So it's a distance, not a time. Star Wars gets that mixed up sometimes. Sometimes they talk about it as a time unit. Not. So let's say I get on my speed, on my light, traveling, spaceship, driving along, speed of light. Look out! That's pretty quick. Okay. You get there, it'll take you 4 Earth years. You can hang out for a little while, you got to chill. You just went 4 light years, for crying out loud. You have to go and get back and chill, see how the things are going on, what's happening there. Go up and get some Proxima Centauri ice cream. So good, so good. You come back 4 more years later, say a round trip, you're gone for 9 years. On Earth, well, that's what it's called the twin paradox, because let's say one twin is on the spaceship, one twin's hanging out back home waiting for their sibling. So 9 years has gone by on Earth. How much time for the person traveling at the speed of light? Answer, 0, none. What? They haven't aged. They would come back and go, hey, man, I wasn't even gone. And the person on Earth goes, yeah, you were, like 9 years, hello, see those gray hair I have now? Actually, I got a lot of it. I got that when I had my daughter. That's what girls will do to you. Different story. All right, so what you got going on there is a time dilation, a time change, depending on the person and the observer. So this is cool. The closer you get to the speed of light, traveling the speed of light, actually, technically, you can't travel the speed of light. You can't do it. E is equal to mc squared, actually, is the reason why. E is equal to mc squared is such a cool equation. So many things you can do with it. Energy and mass are the same thing. You can calculate the mass effect and the binding energy with it. But also, it tells us that the faster something moves, this is cool, hang in there. The faster something moves, the more massive it is. What are you talking about? If something is sitting there, it has a rest mass, it's called rest mass, okay? Its mass is what its mass is. Put it on the balance, mass it, good. But if something is moving, it's more massive. What? What do you mean more massive? Yeah, it is. It's more massive. This is theory. This has been verified. This is not science theory. This is science fact. Been verified. Did experiments with this back in the 50s when jets were able to go fast enough and they had sent out enough clocks in order to measure this. But what ends up happening is, the clocks were measuring the fact that if you go faster, time slows down for you. Also, that mass increases as you go faster. Well, this is just so cool. Why are you saving this the last few minutes of your last video to tell me all this cool stuff? I know, right? Check it out on your own if you have time. But what you got going on is, the faster you go, the more massive something becomes. The more massive something becomes, the more energy you're going to need to continue to accelerate it if you want it to go faster. So as you approach the speed of light, the mass of something goes up exponentially. So this is mass. No, this is mass, sorry. Wrong line. And this is speed. This is velocity. As you travel faster and faster and faster, getting toward this, let's say this is the speed of light right here, SOL. If you're up a creek without a paddle, you're SOL. but I know, it's funny. But no, this is speed of light. So once you approach the speed of light, you're going faster and faster and faster. The mass of you just goes shoo. You get to be so massive that the amount of energy you need becomes infinite. You can't travel faster than the speed of light because the mass of the object becomes infinite. You need infinite energy in order to accelerate it. Just whoa, so many, like, rocking my world here. I know, I get it. I'm trying to do this quick too. So you can't travel faster than the speed of light because according to E equals mc squared, the mass of something as you travel faster and get closer to the speed of light becomes so massive you need infinite energy in order to keep accelerating past that point. Whoa. So yeah, so you can travel the speed of light, but let's just say you're traveling close to it. and you get closer. What happens for you also is the time changes for you. You as a person in that spacecraft would not realize that time back on Earth is ticking away. You'd be kind of going, oh man, I was just gone for like 3 days or something. What are you talking about, 7 years? You know, I was only gone for 3 days, and I went to Alpha Centauri, hang out, ate some Alpha Centauri ice cream. It was great. They have a main black bear on Alpha Centauri too. You should check that out. It's great stuff. And then I came back 3 days later. Why are you 7 years older with gray hair? Why? Good question. This video is approaching a half hour, but I just kind of, this blew your mind, didn't it? That's what we're going to end up with the whole course, blowing your mind with time dilation. Okay, so the faster you travel, the slower time goes for you, and the more massive you become also. Look at me, I'm so massive, I'm moving. Oh my God, you're huge, you're like Arnold now. You're so massive. Oh, what happened to you? Where'd you go? I don't see you anymore. Oh, there you are, you're so massive. Okay, kids, bye. Bye, it's been fun. Bye. Bye.